So three has come. Varun, Rohit, and
Good morning,
Kiran.
sir.
Good morning. Good
Good
morning.
morning, sir.
Good morning. Good morning. Here. Right. Okay, right. All of you, good morning. So yesterday we were discussing the thermal stresses that are induced in the composite bar. So we have to consider two, because given in the problem we were discussing a numerical problem actually. What happened? Yeah, this was the problem. No, this is not a problem. I think problem. So this is a problem yesterday we were discussing. A steel tube was enclosing a copper bar in the middle, and the initial temperature was 20 degrees centigrade, and it is raised up to 170 degrees centigrade. So what is its effect on the composite bar? As we recollect that the composite bar in which two materials are there, composite bar, by definition itself, the two materials are rigidly fixed to each other, right? So when temperature is raised, one will be trying to expand quicker than the other. Here, copper will be trying to extend more than the steel. So by the effect, by the what is it? What would be the result? Obviously, that copper, which is pulled back by the steel, which is actually expanding slowly. That's why actual expansion of the copper would be finally actual expansion would be lesser than what it would have been when it is free. And in the same manner, while copper trying to move faster than the steel, it tries to pull towards it the steel, thereby subjecting the steel material to tension. So that's why the steel will expand. Actual expansion of the steel would be more than what it would have been when if it were to be expanded freely. So obviously here steel is subjected to tension and copper is subjected to what do you call compression. So here we have to find the areas of cross section of both copper and the steel. So we have to consider two considerations. That is so let's go to the second one first of all. As no external loads are there, only compressive load in the copper and the tensile load in the steel. These should be equated because there is no external load. So that is the first consideration. Sigma C AC equal to sigma SAS. Already we have calculated area of cross section for copper AC and area of steel, cross section of steel, that is AS. Just substitute those values in the equation. From the second consideration, as you look into the screen, as no external loads, compressive load on copper must be equal to tensile load on steel. So if we substitute those values, there is a relation between sigma C and sigma S. That is, stresses induced in copper and steel are related here by substituting those values. So let us consider the second one. So that is coming to sigma C is equal to 0.46 sigma S. Now, let us consider the first one by consideration from above. Actual expansion is equal to free expansion of copper, but that would be reduced by the compressive thermal load, thermal stress. Therefore, free expansion of copper minus amount of prevented expansion due to compression. That is actual expansion in copper, and that will be equal to free expansion of steel plus amount of additional expansion due to tension that is subjected by the pull of copper material. So this should be understood properly. Then the things would be equal. So there are two considerations. One is, as there are no external loads, no physical or mechanical external loads on the bar, only thermal heat is supplied, heat energy is supplied. Therefore, obviously, compressive load in the copper must be equated to tensile load in the steel. So that is one thing. From that, we got a relation between sigma C and sigma S. And second consideration, that is the first consideration as I wrote in that first one. So this should be understood properly. Actual expansion is equal to free expansion of copper minus the amount of prevented expansion due to compression. And that must be equal to free expansion of steel plus amount of additional expansion due to tension. So if we continue this, so we'll get this, convert that into mathematical model. So what is the free expansion of copper? Obviously, alpha C TL. Alpha C is the coefficient of expansion of copper. T is the temperature rise, that is some 20 degrees to 170 degrees, something like that. And L is the length of the bar, how much it was then. Okay, let's see. So this is free expansion of copper. But because it is part of that composite bar, it is along with the steel, therefore the steel will pull it back. So its free expansion would not be, its actual expansion would not be equal to the free expansion. So what amount that is prevented, obviously that is compressive load is stress induced in the copper material. So how to get that? Strain into, so what is that? Strain into original length. Change in the length by the original length is equal to strain. Strain is nothing but stress by Young's modulus. So strain, this is strain E into L. Normally equal to what? Change in the length by original length. So obviously change in the length is equal, obviously strain into the original length. This you must understood properly. So this is the free expansion, and this amount which is prevented by the compressive thermal compression, this must be deleted. This is the prevented expansion in the copper. So here, this is free expansion of steel, alpha S into T into L, minus this is strain in the steel because of this is tensile. So sorry, here it should be plus. Here it should be plus. Somewhere missed. Somewhere missed. Sorry, if you are writing it or not, this should be plus. While typing this mistake. So look at this. Now here I got it right. You look here, this should be subtracted. But here for free expansion of the steel, this amount of, because of thermal tension due to tensile load, tensile stress, this should be added to the free expansion of the steel. So this should be plus here, and this also should be plus, because L is deleted from all the terms. L here, because it can be cancelled off. So that's why this simplification, and here it should be plus. So here now, this is the relation. T common is the alpha C minus this comes to this side. Alpha C minus alpha S is equal to this plus this. This actually should be plus. So this is right. This third one is right. So now just substitute the values in this. Where T is the temperature rise, that is 150 degrees centigrade. This is 150 degrees centigrade. Alpha C we got 1.7 into 10 power minus 5, and alpha S is 1.08 into 10 power minus 5, that is given in the data. And here sigma S, EC is given. For steel it is 2 into 10 power 5 newtons per millimeter square, and this is sigma S. Here you see, okay, sigma C is equal, it is, just look it properly. This is sigma S by ES. This is taken as it is here. And this one is converted this, because sigma C is equal to 0.46 sigma S. 0.46 sigma S. So we have taken common this one, sigma S. And for ES, this is 1 into 10 power 5. This is simple mathematics. I haven't done anything great. Just substitute to the known values in this. One is the given numerical values are given here, and in place of sigma C, because from the what do you call the other consideration, the loads, compressive load and tension in steel should be equated. From that we got sigma C is equal to 0.46 sigma S. So that in place of sigma C, sigma S is brought here. So that is simplification. Now this whole equation is in just one variable. So you can find that sigma S. You just go on doing that. Sigma S, you can get it 96.88 newtons per millimeter square, and sigma C is obviously equal to 0.46 sigma S, sigma C equal to, so multiply that 96 with 0.46, you will be getting 44.56 newtons per millimeter square. So this is the first part of the question has been answered. Okay, the second question is some increase in the length of the composite bar, it is said. That is the actual expansion. Okay, so now let us go to that. So increase in the length of the composite bar. So I think you hope you understand this, because this formulating this, understanding this and formulating this one should be done properly. Then everything will be right. The other things, just substituting the values and you'll be getting all that. So understand those considerations properly. Now let us find the increase in the length of the composite bar. Either you select the steel or let's say copper, because actual expansion of both the materials will be same. So let us see which one I have taken here. So I have taken the copper one. Alpha C TL minus sigma C by EC into L is equal to, so you just put that value, because this is equal to actual expansion in the copper. And if you take steel, what happens? This will become alpha S TL. This would become plus, and alpha S by ES into L. So both will be coming to that only 0.737 mm, because all the values, now that we have got sigma C and sigma S, we are just substitute the values there in the left side one. So you'll be getting 0.337 mm. Had it been just copper, if it is not a composite bar, if it is just just copper, obviously the copper would have been extended more than this 0.737. And suppose, or if it is steel without copper, only steel bar, obviously it would be lesser than this, it would have been lesser than by this 0.737. So as it is a composite bar comprising of those steel and copper, so it is coming to 0.737, the increment in the length of that composite bar. This is the second question answered. So you just hope whether you are making note of all these things in a notebook or not, I don't know. Just try to keep a separate notebook for MOS. Already we are in a serious mode. Already we are into the syllabus, and a main topic has been completed. That is finding the stresses in different bars, like uniformly cross-sectional bodies, stepped cross-section or varying cross-sectional bodies, and principle of superposition, tapering bodies, composite bars, and composite bars, which are subjected to external loads. And here this is thermal stresses on composite bar and individual bars. So many things have been completed, and important is stress strain diagram. That is also important. And moreover, all the terms, the definitions are so important. So whatever you are getting through these classes, uh, make a note of all these things and try to make your own notes. I repeat it. Only one guy out of you people, 7 are attending in general. Only one guy is submitting the assignments regularly. The other guys, please respond. Please don't take it as granted. It is your work, not our. More important is for you. Anyway, we'll get our salary at the end of the day. Maybe for the last 4 months we are not getting any salary. That's different matter. Uh, but anyway, we'll be getting in future all these cumulatively. But it is not about our money. It is your subject. It is the entire exercise is for you. So please do not postpone the things which will overburden your heads later on. So please complete that and just continue to interact with me. Just get into that mode, please. Do not neglect. So let us go to the other topic. So here the lateral strain already we discussed it in the previous classes. Whenever a body is loaded with tensile load, length of body increases. It's very straight. Tensile load, obviously, length increases. We call that as longitudinal stress or longitudinal strain, we can say. Simultaneously, if a tensile load is applied along the length or axial load is applied, length increases. The other phenomena is that in the lateral directions, perpendicular to this length, it could be along the breadth or along the height or thickness, or like if it is cylindrical bar, along the diametrical lines of the cross section, that will decrease. Because along the length you are applying the tensile load, the length is increasing, but in the lateral directions, breadth, height, thickness, depth, or diameter will decrease. That is what lateral strain. Lateral strain and longitudinal strain. Longitudinal strain means you are applying tensile load. So obviously what happens? Length increases. That is increase in the length where the original length is strain. We call it as linear strain, longitudinal strain, direct strain. All these things are synonyms, let's say. So longitudinal strain. Let us because we are comparing it with the lateral strain, we are trying to understand lateral strain in contrast to the other strain that is called. So let us call it as longitudinal strain. Simple strain is called longitudinal strain. So in the lateral directions, it is called lateral strain. So what is the amount of breadth that is decreasing by the original breadth? That is what lateral strain is. The amount of the height that is decreasing and the original by original height or original change in the thickness or by original thickness, like this change in the diameter by the original diameter, that is called lateral strain. And by experiment, so these things I have written there. So it is like this. So you just look at the figure. So length is increasing, but the, let's say the height of that rectangular bar is decreasing. So that would be the phenomena. So height, I have third dimension I have not shown, only two dimensions, that is length and height I have shown here. So length is increasing, but whereas the dashed ones, whereas the height has been decreased. So this is simultaneous. We are not doing anything yet. We are just applying the tensile load, and these two things will happen in the direction of the force or the load, or in the lateral directions. These things happen. So there is another term, Poisson's ratio. What is Poisson's ratio? By experimentation, by observations through experiments, in any material, when loads are applied within the elastic range, always do keep that in mind, within the elastic range only. So what is Poisson's ratio? This is there is a what do you call relation between that longitudinal strain and the lateral strain. So that defines the Poisson's ratio. It is just the ratio of lateral strain to longitudinal strain, and it is denoted by mu. It is the ratio of lateral strain to the longitude. Lateral strain will be in the numerator and longitudinal strain would be in the denominator. You just make a note of it. E lat, when I write lateral strain, I think I have E lateral. Mu is equal to E lateral by EL. So obviously, so how it would be? By experimentation. So you just look at this. It is a material property. So for each material, it's a unique value. It carries a unique value. It has a unique value for each material. So in generally, that mu, which is called Poisson's ratio, which is the ratio between the two strains, that is lateral strain to that of longitudinal. Okay. So overall, the mu will be ranging between, it lies between 0.25 to 0.33. Somebody has come. Okay, Mahesh sir. So the lateral strain, the Poisson's ratio will lie between 0.25 to 0.33 for all the materials. Normally, it will be in this range. Just look at that. It is always less than 1. Suppose you are doing some numerical calculation to find the Poisson's ratio in the middle or as an end answer. If you are getting something more than 1 or more than 5, more than 0.6, like that, obviously you must cross check your calculations, whether you have taken it right or not, because it is a property, material property, and for all the materials, it has its own unique value, but all those values will fall between 0.25 to 0.33 only. Only for rubber, it is 0.4 to 0.45. You just remember this. As I said, when you do the numerical problems, if you are getting the Poisson's ratio beyond this range, either lesser than the least value and let's say lower limit, or if you are getting more than the upper limit, that is more than 0.33, obviously you need to check your own calculation. So this is one more thing new, right? Now, let us, taking these things into account, let us find stress-strain relationship in one-dimensional stress system, two-dimensional stress system, three-dimensional stress system. What do you call? How do you then it? Let's see, first take for one dimension. Already we have taken stress strain relationship through the diagram, and particularly we have considered a material mild steel, which is a ductile material where the behavior of the material under external loads is visible very significantly to us. That's why we have selected that mild steel material, and that is one way of looking at things. It is constantly studying the behavior. For numerical problems, for analyzing quantitatively, that is taking the values. So we'll be studying in the other form, that is stress strain relationship, but let us take for one dimensional stress system. Now, this is one dimensional stress system means I am just stressing the body in just only one direction, that is in the length direction. Just look at that sigma. There is a prismatic bar where length, breadth, and height are there to that body. Prismatic bar, rectangular bar, you can say. The cross section may be normally rectangular, or it may be square cross section as well. But I am subjecting this bar only in the one direction, that is load applied in the axial load. The axial load, let's say here it is tensile load also from the figure. But there are three other directions. X is the length direction, if we say. So Y is that is this one, as it is shown here. This means this one. This is the breadth, and obviously this is the direction, height direction. So that is what I'm trying to say. So obviously length increases. So strain in X direction, what would be strain in X? It is straight, just sigma by G. Because what is the strain in the X direction? It is sigma by G, stress by Young's modulus. Or if you bring this one, stress by strain is equal, you take this on the other side, you will be Young's modulus. Stress by strain is Young's modulus. That's why I've taken here strain in X direction is sigma by E. Next, in the similar manner, what is the strain in Y direction? As I said, simultaneously that phenomenon occurs. In the lateral directions, the dimension decrease as we are applying here the tensile load along the axis or along the length. So that is strain in x direction is sigma by g, but strain in y direction obviously takes minus sign because it is decrement. So I have taken this. So this is lateral strain, and if you take this one, longitudinal strain. So that is equal to mu. The ratio between lateral strain and the longitudinal strain is mu. If we bring it here, this is the equation. But as this is decrement, the strain will be taking the negative side. So that is equal to minus mu into sigma by instead of Ex. That is longitudinal strain. I am bringing this here. So this is how you have to analyze. So this is for the one dimension. In the same here, it is very clear. Strain in z direction as well. I'm just forgetting it. Is z. So that is in this direction. Obviously, that also will be taking the same. This is z by, let's say, this is Ex, mu x only, minus mu Ex. Ex is sigma by, because it's only one stress, that is one strain longitudinally. So obviously in the lateral direction, what is happening? Mu into longitudinal strain. So that is what these two would be same if it is one dimensional stress system. Just this is to start with. Normally, we don't have this simple stress system normally. So when we go into the actual practice, it would be a system of forces. That means the stresses would be induced in different directions. So that's why to start with, we have selected this just one dimensional stress system where just one load is applied along the length. So obviously longitudinal strain is induced in that. Obviously it would be plus, and that is Ex is equal to sigma by E. But in the Y and Z direction, that is breadth and let's say height directions, we got that is minus mu into sigma by E for both of these. And from this, let us go for the second one, two-dimensional stress system. Just look at the figure again. So it is lengthwise, it is subjected by stress sigma 1. That is subjected by a stress sigma 1 means what? Obviously, a load is applied in that direction. So load by cross-sectional area. Cross-sectional area is obviously, for this one, this is the cross-sectional area. This entire thing is cross-section for this load. And for the other load, so another load, it is subjected in the other direction, breadthwise direction as well. That is Y direction as well. So it is sigma 2. That means a load is applied perpendicular to the length, that is in the breadth direction. So that load by this area of cross section is obviously equal to sigma 2. So this body is subjected to two stresses which are mutually perpendicular. One is in the length direction, or let's say here X direction, and the other one is Y direction. This is X direction and Y direction, X direction and Y direction. So how to do it? It is just tedious job. Only thing is you should not miss in the middle. It's very simple only. So only thing is, if you do some paperwork, that is you put your pen on the paper, then only you will be having some grip over these things. It is just a tedious job. It looks simple when we understand this, when we try to understand this, but later on, if you try to, all of a sudden, if we want to solve some numerical problems, definitely we may get into some sort of confusion without a good practice. So continue to do practice. So let us take the first one. That is strain in X direction. What happens? It is very important here. If we can understand this, then the next one, that is three-dimensional stress system, will be much more easy. The stress-strain relationship between for a three-dimensional stress system. Now here already we have discussed the first one. We are going for this one. So strain in X direction for what? Strain in X direction. Strain in X direction. So time is running out. Let's say strain in X direction is simple. Try to keep it simple. One is due to sigma 1. The strain is sigma 1 by G. It is very simple, because strain is equal to stress by Young's modulus. It is strain in X direction, but in X direction, sigma 1 is acting. Sigma 1 is acting. So what is the strain? Longitudinal strain plus takes, because its length increases, therefore strain is plus. That is sigma 1 by G. But due to this force in the other direction, this is another force. This is another stress. due to this in its own direction, that is breadth direction, it increases like this, sigma 2 by E. But in the x direction, the length gets decreased due to this one. That you must understand. So that takes to, because due to sigma 2 in the y direction, what is the lateral strain? For breadth direction, length will become lateral direction. Are you getting me? Because this is breadth direction where sigma 2 is acting. For this load, for this stress, this will be lateral direction, perpendicular to this. Perpendicular to breadth is length also. So due to sigma 2, a negative strain will happen, that is mu into sigma 2 by E. In its own direction, what happens? In y direction, this is strain in y direction is sigma by 2, that will happen. But strain in x direction, there are two stresses that are being subjected to. There are two stresses are applied on this. So because of this sigma 1, it is a positive strain. Because of this sigma 2, a negative strain, which takes mu into sigma 2 by E, because it is less lateral strain due to sigma 2. So this is strain in x direction, cumulative. The net strain in the x direction is this much. In the same way, strain in y direction, because of its own direction, we are finding to trying to find the strain in this direction, in its own direction, sigma 2, that is sigma 2 by G, because it is tensile, it takes positive. But due to this sigma 1, its effect in the lateral direction, that is in the y direction, it would be negative. That is mu into sigma 1 by E. Just look at these two terms carefully. So this is very important. So what happens due to this sigma 1 and sigma 2 in x direction and y direction, it is being stressed. And what is their cumulative effect in the z direction? So that is what it would be next one. So due to sigma 1, because for both sigma 1 and sigma 2, z direction is lateral direction. X, Y, Z are three mutually perpendicular directions. You know that, length, breadth, and height. So we are here trying to find the strain in Z direction, height or thickness, let's say. So because of the in its own direction, there is no stress. In Z direction, there is no, it is not stressed. So there is that, this type of figure is absent. So due to sigma 1, the height decreases. Due to sigma 2 also height decreases. That is minus mu into sigma 1 by G minus mu into sigma 2 by G. If you take this mu by G outside, minus mu by G into sigma 1 plus sigma 2, we can write it as like that. So these two, from first you try to understand this and then you try to understand this. So if it is one-dimensional system, in one direction sigma is applied and its effect in both its own direction, in the other two directions, we have found out. Strains we are trying to find. Why we are finding the strains? Obviously, what would be the change in that breadth? What would be the change in the height also? When even you can apply even one force, one stress, you can subject it to, or you can subject it to two stresses in two directions, or you can subject it to three directions, stress in three directions. So that we are going further. So I'll go in a quick manner. Let's say that the figure I have not drawn here. Okay, let's say. Okay, anyway, I think from that you can easily get that. Just look at the figure. So sigma 1, sigma 2 here. Sigma 1 in this direction, sigma 2 in this direction. Obviously, sigma 3 will be applied onto this roof or this bottom. So it acts in this direction, it acts in this direction. It is pulled in this direction. Sigma 3, let us take like that. I have missed to write the figure. Not missed, but just shifting it here. So three-dimensional stress system, obviously, just you give a thought to it. Due to its own, the stress in its own direction, it would be positive sigma 1 by G, because we are applying tensile stresses only. So in the other two direction, it leaves, this sigma 1 leaves a lateral strain of this. Obviously, it takes negative. Sorry, in its, okay, that will be coming later. Due to the other sigma 2 and sigma 3, a lateral strains for these sigma 2 and sigma 3 What is the lateral one? Obviously, x direction is lateral 1 for those sigma 2 and sigma 3. So due to the sigma t, this is the lateral strain which is which would act in the x direction, and due to sigma 3, this would be the lateral strain which would be acting in the x direction. So this would be positive due to the stress in its own direction. Due to the stresses in the other directions, a lateral strain occurs in the x direction, so that would be taking negative sign. So overall strain in x direction would be this much due to all the three, sigma 1, sigma 2, sigma 3. In the same manner, in y strain in y direction, you look at that. So now y direction, which is the positive, obviously sigma 2 will be positive. And due to sigma 1 and sigma 3, it would be negative. So you have to write these terms properly. Okay, sigma 1, due to sigma 1 in y direction, obviously a negative lateral strain will occur. Due to sigma 3, a negative strain occurs in y direction. In the same manner, in z direction. Here it is sigma 3 also is coming into picture. Therefore, sigma 3 by E would be positive in its own direction. But due to sigma 1 and sigma 2, a lateral strain occurs in z direction. Therefore, this is. So each term coming for 2 times, I think. So we are done. So why we are all doing all this? After finding strain in each of the directions, multiply by original dimension in respective directions. Suppose say you are subjecting a bar with those 3 loads in 3 different directions. And you will say, you will ask, what is the change in the breadth? So you will have to write this expression. So stress you all find, Young's modulus will be normally given and mu will be given. So you will be writing all this. So you will be finding sigma 1, sigma 2, sigma 3, Young's modulus, and you will be finding by substituting those values in what is strain in the y direction. This is strain in y direction. Strain into y direction, sorry, strain in y direction into the original breadth. Strain in breadth, y direction means breadth, let's say. So strain in breadth is this much. You compute this one by writing these things. And then multiply it with the original breadth. Thereby you will be getting the change in the breadth. If it is positive, the breadth will increase. If it is negative, if the strain coming to be negative, the breadth decreases, overall breadth. After simultaneous application of those 3 stresses, let's say a force system which is comprising of 3 forces in the 3 mutually perpendicular directions. So that is the objective of this, finding the strain in x direction, strain in y direction, strain in that direction. That is to find the changes in the length, change in the breadth, and change in the height or thickness. And if we take all this, okay, time is running out. Later on, what will you do? Obviously, if change occurs in length, breadth, height, or diameter, let's say, what happens? Obviously, volume changes. Volume changes. So obviously, change in volume by the original volume will be equal to volumetric strain. So volumetric strain into original volume obviously will be change in the volume. So in order for that, we have discussed all these things. So later on, we'll be finding that volumetric strain also, next class. Okay. So please guys, only one guy has sent me the, assignment, let's say a small assignment. So I'll be giving a big assignment later, but on each day, if you complete all these things, because today we have discussed that numerical problem, we have finished off that, completed fully today. So you just write them. You may think that it is a very simple one while listening, but later on what happens, definitely unnecessarily don't put yourself into a complicated situation, right? Don't make the things complex for you. So this one, you please do it. I may be sending, if I find time, I'll send today itself some other questions as well. But at least what we have discussed